Hello everyone and welcome to today's webinar. Today's webinar is titled An Analysis of Hip Joint Contact Forces in People with Femoroacetabular Impingement Syndrome During Squat Tasks. My name is Christopher Iversen and I work here at Anybody Technology. And I'll be the host of today's webinar, which is the session 2. We also had a session a few hours earlier, so this is session 2 of today. In the Anybody webcast series, we host presenters who have worked with the Anybody modeling system to cover different use cases. And in today's webcast, we have an external speaker, Mattia Perron from Rush University Medical Center. In this webcast, Mattia will present his and his colleagues' findings on whether hip joint forces during squat tasks are altered in people with femoroacetabular impingement syndrome. And this presentation will start in a minute or so. But just before we start, I will give you a general introduction and overview of the Anybody modeling system for those of you who are unfamiliar with the software or musculoskeletal modeling and simulations in general. So first of all, I would like to draw your attention to the control panel, which appears on the right side of your screen. And you are very welcome to submit questions and comments via the questions panel during the presentation. And we will try to address the questions at the very end of this webinar. And in case we do not get to answer all of the questions, I'll try to do so by email within a reasonable time. So let's begin with having a look at what the Anybody modeling system actually is. Well, the Anybody modeling system is a software that allows you to do musculoskeletal modeling and simulations. As input, it takes motion data as kinematics and forces, and it calculates the internal body loads as joint reaction forces, muscle activity, and metabolic energy. And at the moment, Anybody is used in a wide variety of areas and applications. And a few examples of this is movement analysis, product optimization design, the field of sports optimization, orthopedics and rehabilitation, ergonomics, which could be with and without assistive devices, as for example an exoskeleton, and also in the automotive industry. And the typical workflow in Anybody could look something like this. So you provide the recorded motion data as input and use the body models which you or others have built. And then you can provide some kind of environment, which could be a special type of equipment or an exoskeleton, as it is in this example. You can then use Anybody to combine these things, solve the muscle recruitment, and run the inverse dynamics simulation. And this basically means that we go from motion to calculating the internal body loads and the interaction with the environment in some cases. You can then output the results and use it for some kind of post-processing with, for example, a finite element tool. But many users also choose to close this loop completely by doing some kind of design optimization and then run this cycle multiple times. And this actually brings me to the end of the introduction. I'll hand over the word and present the role to Mattia instead.
Hi everyone, I'm Mattia, and the title of the presentation of today is An Analysis of Hip Joint Contact Forces in People with Femoroacetabular Impingement Syndrome During Squat Tasks. Okay, so I would like to start with an outline of the presentation of today. So we will be discussing, first of all, background, especially in terms of the pathology that this presentation will deal with, which is called the femoroacetabular impingement syndrome, or FAI, which is a hip condition. And I will also talk about briefly musculoskeletal models, so basically the methodology that we used to analyze this kind of patients. In the method section, I will focus more specifically on musculoskeletal models and in particular to the framework that we use in the current investigation, which is the Anybody modeling system. In the results and the discussion section, I will present the main findings. So basically the biomechanical variables, the most meaningful biomechanical variables that we obtained, and I will discuss them. And finally, in the conclusion, I will summarize the key aspects of the presentation. Okay, so before starting the presentation, I would like to acknowledge that this study was recently published in Journal of Orthopedic Research. The findings that were published there are actually, let's say, part of a broader study that involved also my master's thesis. So I would like to acknowledge also all the institutions that are involved in this project. So Politecnico di Milano and University of Illinois at Chicago, which are directly involved into my master's thesis. Also Arcadia University, since I was a research assistant there while I was conducting this investigation, and of course also Rush University, which is my current affiliation. Okay, so let's start with some background. We'll start with the pathology, as I was mentioning before. So femoroacetabular impingement syndrome, or FAI. It's a hip condition. It consists in premature contact between the proximal femur and the acetabulum. You can see here an example on the right-hand side of the slide. So there is an abnormal morphology of these two bones, and which leads to the so-called impingement. And this may result in altered and abnormal kinetics and or kinematics. It has an incidence, this pathology has an incidence of about 20% in young athletes and active adults, considering the US population. So a pretty important incidence in terms of young and active people. Okay, so let's say that there are different tests that can be performed to analyze this kind of pathology. In general, we are interested in exploring kinematics, how, let's say, in these patients, kinematics and kinetics are affected. So there are different kind of tests that can be performed. One of these kind of tests consists in vivo test, which basically means replacing the joint, so the hip joint, with an implant. Of course, this is something that is feasible just in some specific patients because it's a highly invasive procedure. So it's still an option, but it's not, let's say, something that can be applied always. Then we have in vitro test. This may mean, for example, extracting some cartilage from the let's say, injured side, where the impingement occurs. This is something that, again, can be done, but has some limitations because it doesn't allow, or at least it's more difficult with this kind of test to reproduce a real life motion task, like, for example, gait or stair ascent. And then we have also in silico test. In silico tests are pretty commonly implemented and used. They have some advantages both with respect to in vivo test, because they are much less invasive, and also with respect to in vitro test, since they allow for easier, let's say, reproduction and reproducibility of real motion task. Okay, so here a brief introduction into musculoskeletal models, which are an example of in silico test, in general in silico models. So musculoskeletal models include the representations of bones, joints, ligaments, and muscles. And you can see here an example on the right-hand side of the slide. They receive as input data kinematics forces, and as output data joint moments, muscle forces, and joint forces. That's a really quick overview of these kind of models. I will talk about them more in depth later on when I will describe the specific framework that we implemented and we used actually for this investigation, which is the Any-Body Modeling System. Okay, now I would like to focus on some specific studies that you can find in the literature dealing with the implementation of musculoskeletal models for patients with FAI. Specifically, I would like to focus on the different kinds of motion tasks that are analyzed. We will start here with gait, which is the motion task that is actually most commonly investigated, I would say, in general in motion analysis studies, and also for this subset, so musculoskeletal models for patients with FAI. One important thing about gait, and I will talk about it also later on in the presentation, is that hand of hip range of motion is not involved, and also it's important to underline the fact that inconsistent results in the literature are obtained concerning gait. So what does this mean? The idea is that most of these studies implementing musculoskeletal models for a specific pathology then focus on presenting specific results, which consist basically in biomechanical variables, which could be, for example, moments, forces, or also angles at the joints of interest. The idea is that these studies want to show if there are any differences between these biomechanical variables in controls and in patients. And so basically the fact that inconsistent results are obtained means that some studies for the same biomechanical variable found some differences between patients and controls, maybe in terms of the peak values of a biomechanical variable or of the overall shape throughout the motion task, while others do not find any differences. So there is some kind of inconsistent results. Some studies found differences, but other studies didn't find any differences. This is actually true, for example, about gait. Then we have double X squat, which is a motion task less investigated than gait in this framework. And the deep range of motion is reached in double X squat, and again, this is something I will circle back later on in the presentation. And low forces at the hip are involved, again, a key point. And then we have single leg squat. So single leg squat is a motion task that is actually not really investigated, not commonly investigated in this framework. And of hip range of motion is reached in this case, as happened for a double squat. But in this case, we have high forces at the hip. Again, this is a key point. Okay, so what's the aim of this study? The aim of this study is to compare hip joint forces during gait, double leg squat, and single leg squat between healthy controls and patients with FAI. So here I've just mentioned hip joint forces, but actually we analyzed different kinds of biomechanical variables. We also studied moments and angles in the 3 planes. I just wanted to focus on hip joint forces because most important results of this investigation will deal specifically with this biomechanical variable. But I will also present some other findings specifically in terms of hip joint angles. We also conducted a further analysis in terms of comparison between healthy leg and injured leg within patients with FAI in terms of hip joint forces. And our initial hypothesis was that hip joint forces would be lower in people with FAI. So that's a pretty reasonable hypothesis, since these patients may experience pain while performing specific motion tasks. So this may be, let's say there may be some kind of defense mechanism that they will have in order to minimize the forces of the injured hip. Anyway, this is just an hypothesis. We don't know if this is true. And most importantly, we don't know where it would be true. So we don't know if maybe there are lower forces during gait, during double leg squat, or during single leg squat, or in all of these tasks, or in none of them, especially because, as I was saying before, there are some contradictory results in terms of biomechanical variables. So we wanted, let's say, to have a better understanding of the overall situation. What's the overall the long-term goal of this study? The idea is that if we are able to show that there are actually some differences in terms of forces of other biomechanical variables between patients and controls, then we can use this finding and also combine them with other, for example, clinical outcomes or imaging findings or pain and symptoms by specific subjects. And we can use also these musculoskeletal models as a supportive framework and tool to diagnose people affected by FAI. So that's, let's say, the long-term goal in which this study can be placed. Okay, so now we'll talk about the methodology that was used. Here you can see the motion capture pipeline that was followed. Pretty standard motion capture pipeline. We start with the acquisition system. So we have force plates and 14 infrared cameras, which detected respectively ground reaction forces and the market trajectories. So just to go a bit into the details, the idea is that when a subject performs some motion capture test, let's say, they are instrumented with some reflective markers, and then they are asked to perform a specific motion task, which could be gait or squat, like in the current study. And while they're performing this task, there are infrared cameras that detect the position of the reflective markers throughout the trial. Then we have force plates. The force plates are able to detect the ground reaction force, so the force between the subject while he or she is performing the motion task and the ground. And these are the two main data, let's say, that are acquired. and then also processed through a specific software that is called Motive of Track, or at least is the one that was used in the current investigation. And then C3D data are provided as output from Motive of the Track. They are the input of the antibody pipeline, so this green box that I will discuss in the following slide. And then we have post-processing of the output from antibody. So for this specific study, it joined forces, angles, and moments. We use a specific tool called the NIPI tools, and also conducted some post-processing in terms of the statistical analysis in MATLAB. Okay, so that's the antibody pipeline, the green box I was mentioning before. There are 3 steps that were carried out in this context, and these are the parameter identification, marker tracking, and inverse dynamics. So first of all, we imported the musculoskeletal template geometry from the AMMR, the Antibody Managed Model Repository, which is basically a library, a collection of different models. We used the TLEM, so 20 lower extremity model version 2.1, which was the newest one at the time of the investigation. And the idea is that the parameter identification scales this musculoskeletal template geometry according to the information within the static motion capture trial. So static motion capture trial is actually a C3D file, C3D data. I showed it in the previous slide, I was mentioning it. And during the static motion capture trial, a subject is just staying still. And the idea is that we can use the information from this trial to scale the musculoskeletal template geometry. So for example, the length of the arm or the length of the leg and something like this. So after the parameter identification, we would have a body model scaled according to this input data. And that's actually also the input for the next step of the pipeline, which is the marker tracking or inverse schematics. Marker tracking so receives this body model scaled, and also a dynamic motion capture trial. So this is again actually a C3D file, and in this specific file, the subject is actually performing a specific motion task, like gait. And the output of the marker tracking are joint angles, which are then provided as input to inverse dynamics. And they're combined also with the same dynamic motion capture trial for inverse dynamics. Inverse dynamics provides as output joint forces and joint moments. Okay, so as I was saying before, the model that we use for the current investigation is the 20 lower extremity model, version 2.1. Here, I just want to briefly mention some of the files that we used and, let's say, modified for the investigation. So there is, for example, in Antibody, there is a specific file related to the trial that has to be performed. So the trial specific data.any file, in which you can select the C3D file you want to have in input, as well as the initial and final frames. Then we have also the subject specific data.any, so to enter some information in terms of the subject that is performing the motion task, like anthropometric measurements such as body mass and body height, and also the marker protocol.any, in which marker protocol tuning can be performed. So without going too much into the details about especially the last file, but I can describe, let's say, the marker protocol tuning as the operation of match between the marker protocol that is implemented in Antibody and the one that is basically used for motion capture trial. So the one that is also within the C3D file. Here on the right-hand side, you can see the marker protocol that was used in the current investigation. So you can see the in red, you can see the markers that were used just for a static trial. In black, the one that were used just for dynamic trials. And in blue, the ones that were used both for static and dynamic trials. So in general, for all the static trials, just red and blue markers were used, while for dynamic trials, both black and blue markers were used. Okay, so I mentioned a few slides ago that we analyzed 3 different motion tasks, so gait, double export, and single export. Now I would actually like to show you how, let's say, do this task look like in the antibody interface. So you can see gait, you can see double leg squat, and you can also see single leg squat. So in terms of the participants of this study, there were 10 controls, so 10 healthy people, and 10 patients with FAI for gait. 10 controls and 10 patients with FAI, again, also for double leg squat. And for single leg squat, we had 8 controls and 8 patients with FAI. Specifically for single leg squat, we also conducted an analysis in terms of the comparison between healthy leg and injured leg within patients with FAI. So actually, we had 24 overall measurements, so 8 for controls, 8 for patients with FAI considering the healthy leg, and 8 considering the injured leg. Okay, so now we'll talk about the results. So in this slide, and also in the first one, and the next one, sorry, I would just like to show an overview of the graph, especially in terms of the how to, let's say, read them, how to interpret them, and I won't be really actually focusing on the clinical meaning of these findings. So, for example, you will see many other graphs like this, and I'm referring specifically to the one on the left-hand side. So every graph will have on the x-axis the percentage of the motion task cycles. So in this case, we have the gait cycle. On the y-axis, there will be the biomechanical variable that was analyzed. In this case, we have sagittal plane, hip joint angle, so flexion extension. There are, you can see that there are 2 black lines here. They are basically the mean of the observations that we had for each cohort. If you recall, for gait, we had 10 controls and 10 patients. So these 2 black lines are basically the mean of these 10 observations, let's say, each. And there's also this shaded area. The blue one is the standard error for patients, while the red one is the standard error for controls. Then if we look at the graph on the right-hand side, it contains some information in terms of the statistical analysis that was performed. So that's statistical non-parametric mapping, and basically consists in performing the test for each of the points of the time series. And the idea is that if this black curve does not overcome one of these 2 thresholds that you can see here, so these 2 red dashed lines, then it means that there are no statistically significant differences between the curve on the left-hand side. And this is actually what happens here, because you can see that this black line stays in between these two lines, and so this can also be confirmed, let's say, from a qualitative point of view, let's say, overall. This is another example. Again, just want to show in general the pattern, not really focused on the clinical results. But you can see here that the graph on the right-hand side, the black line overcome this threshold, this red threshold, roughly from 60 to 80% of the cycle. In this case, this is a single leg squat, so single leg squat cycle. And so you can find, let's say, this correspondence also in the graph on the left-hand side, which is, let's say, marked by this yellow area. So the yellow area is where there is some statistical significant difference between the 2 curves, so the blue one and the red one. And in the next slide, I will show graphs just about like the one of the left-hand side of the slide. Okay, so here we have some actually interesting results that I would like to discuss. Specifically, these are comparison of hip joint forces during different tasks. So we have gait, double leg squat, and single leg squat. These are hip joint forces normalized by body weight, and we focus specifically on the proximodistal component of hip joint forces because it was the one like conveying more meaningful results. So first of all, I would like to draw your attention on the values on the y-axis. For gait, peak values here are obtained. The values are about 5 in terms of peaks. For double leg squat, they're about 3.5, while for single leg squat, they're much higher. They're about 9 for controls and about 7 for patients. So that's the first thing that we can notice, let's say, starting from these graphs. The second thing is that we can see this yellow area just for single leg squat. So this means that there is a statistically significant difference just during single leg squat between patients and controls. We can infer that this difference occur because of the magnitude of the hip joint forces, proximodistal hip joint forces. In fact, we can see that patients seem not able to withstand forces that are higher than roughly like 7, and so when the motion task would require a force that is higher than this threshold, they're not simply able to withstand it. While this does not happen to controls, as you can see here, because the peak values that are reached are not that are actually higher. So we can reach about 8.5. We don't see any differences in terms of peak values and also, let's say, overall shape between patients and controls in terms of gait tasks. We do see some differences actually in a double leg squat, but they are not significant. And so, let's say, this is also justified by the fact that hip joint forces are lower. So this is the reason why we don't see any statistically significant differences. I will circle back, let's say, to the difference that we can say that we see here later on. Okay, so in this slide, we want also to include an analysis of the kinematics. So to relate the differences in terms of hip joint forces with the differences also in terms of hip joint angles. And specifically, we focused on sagittal plane hip joint angles because this was, let's say, the most interesting biomechanical variable. So in the first column, you can see basically the same graph shown in the previous slide. So again, hip joint force proximodistal. Second column, you can see sagittal plane hip joint angles, so the kinematic variable I was mentioning before. First row double leg squat, second row single leg squat. Starting from what we were saying in the slide before, higher forces experienced by subject while performing single leg squat. So this leads to differences just for single leg squat between patients and controls. We don't see any statistically significant differences between patients and controls for single leg squat. And if we look at the graph in the second column, we can observe that for single leg squat there are some differences. You can see that these differences occur mainly from 60 to 80% of the single leg squat cycle, which is also roughly where we had differences in terms of forces. Why do we have these differences? The idea is that if we have higher forces in single leg squat, then patients are not able to withstand such high forces, and so for this reason they will perform squats that are less deep as the one that are performed by controls. And so here, for this reason, we will have a lower sagittal plane hip joint angle. It's interesting to compare these findings with double leg squat, because you can see that actually in this specific graph, so the one on the top right, there are no differences in terms of peak values, both between patients and controls. They both reach about 120 degrees. And also, I would say that the overall shape of the curve is pretty similar, and this can be explained by the fact that there are lower forces here in double leg squat, and so for this reason, the patients do not have to perform squats that are less deep with respect to controls, because they are able to withstand such forces. Then, of course, the impingement anyway can play some kind of role in this for these patients. You can see here that there are some differences in terms of peak values, even though they are not statistically significant. But this can be related to the fact that for double leg squat, we do have the end of a hip range of motion that is reached, while, for example, in this previous slide in gait, we don't see the end of hip range of motion, so maybe we have less impingement, and so we have also less differences in terms of peak values. In this slide, basically, we have pretty similar findings to the one that I showed before. So double leg squat row is actually the same. Single leg squat, we include an analysis of basically a comparison between healthy leg and injured leg within patients. So actually the blue curve is the same on the previous slide. The red one here consists in the healthy leg instead of the controls. But you can see that basically the main findings can be observed also here. We still have differences, statistically significant differences in the same part of the single leg squat cycle, actually both in terms of forces, hip joint forces, and also in terms of angles. You can see here again from 60 to 80% more or less. And so basically this is a further confirmation of what we were saying previously. So when these patients use the healthy leg to perform squat, they're able to withstand, say, higher forces, while this does not happen when they are performing the squat with the injured leg. And this occurs just during single leg squat. So discussions, I've actually already talked about the graph, but just want to highlight, let's say, the main points. So single leg squats, we have lower proximodistal hip joint forces in patients with respect to controls. As I was saying before, it's, I think, the key point of the presentation. And so this is a strategy that's adopted by these patients to avoid pain during this high demand task, which is single leg squat. And here you can see the corresponding graph. For single leg squat, again, lower flexion hip joint angles between patients and controls here in this graph, while for double leg squat, no differences in terms of flexion hip joint angles between patients and controls, the graph on the right hand side. And so we can conclude that the focus should be placed on proximodistal hip joint forces when dealing with patients with FAI. So we have differences in terms of forces in single leg squat, and for this reason we have differences in terms of angles also. When in double leg squat we have lower forces, so no differences between patients and controls, and also, as you can see here on the graph on the right hand side, the curves look pretty similar. Finally, gait and double leg squat, no differences in terms of flexion hip joint angles between patients and controls, so I've actually already discussed it, but anyway, lower proximal distal hip joint forces during this task are experienced by subjects, and so this is the reason why also from a kinematic point of view we don't see any differences. Okay, so conclusions, let's summarize the key points. Background, we focused on the pathology, a specific pathology, which is femoroacetabular impingement syndrome, and also a brief introduction of the methodology that was used for its study, so musculoskeletal models. Then the methods, we focused on the implementation of musculoskeletal models in antibodies, so delineating the whole pipeline that was followed in the current investigation. Then the results of the discussion, here I just wanted to report the key point of the presentation. So lower proximodistal hip joint forces for patients with FAI during single leg squat, which is a high demand task. And then as next steps, there are some possibilities, like more complex model can be implemented, like for example, implementation of subject-specific hip geometries for MRI reconstruction, and also analysis of hip muscles behaviors from EMG data can be done, maybe also to like further validate the results from the study. So basically comparing the EMG data that are acquired in terms of muscle activation with the ones that can be also found using the antibody modeling system. So that's it. Thank you for your attention. If you have any questions, I'm happy to answer.
Thank you very much for the presentation once again. So just before we go to the Q&A session, I would like to say a few words about our online resources. So let me just share my screen. There we go. So if you want to know more about Anybody Technology, then you can go and check out our website, anybodytech.com, where you can find different events, special dates, and also all of our previous webcasts. There is a big library, which we call the webcast library, where you can go and filter based on the area you are interested in, and then you get all the previous webcasts we have held there. We also have a community website called anyscript.org. This is really for people using Anybody. And here you can find multiple online resources as our wiki page, several blog posts, and also links to our repository sites. It's also here our forum is located, so you can go and ask questions and get help from fellow Anybody users. But we also tend to look at the forum from time to time and see if there's any questions we can help answer. Then I would like to highlight an upcoming webcast on March 21st, so it's actually quite soon. But we have finally released our next software version Anybody 8.0. So you can tune in and join us for a tour of the new Anybody modeling system, but also the included updated Anybody managed model repository 3.0. And the registration for this is already open on our website, so you can go and sign up. And if you are using Anybody or just interested in seeing what are the news, then I really highly recommend this one, because it gives you like a very good in-depth information about what is really the bleeding edge of the new models. And to end this, I would like to mention that we also maintain a publication list of all of the publications using the Anybody modeling system. And this list recently reached more than 1,000 publications. So this is really a great place to go if you want to get some inspiration on how to use the system and see what have already been done. And similar to the webcast library, then you can go and select specific keywords based on your industry, research area, or even body parts, and you can combine all of those. So you can really combine it, for example, go to sports and knee and finite element analysis, and then it will combine all of these keywords and only give you the combinations which the publication has, the combination of these keywords. So it's really a great place to search for information. And with that, I would like to go to the Q&A session. So thank you for your attention so far, and I'll see what we have in terms of questions.